In this problem, this is an example Hardy-Weinberg problem, and we are going to try to determine the frequency each allele shows up and the frequency of each genotype. This is a situation where we're dealing with a recessive genetic disorder. That means big N, you would inherit and you would be normal. Little n would show the disorder. So they tell us that 1 out of 64 babies born has this genetic disorder. So that means that 1 out of 64 babies born is little n, little n. This corresponds with Q squared. So Q squared is going to equal 1 divided by 64, which will equal 0.015625. Now, from there, we want to figure out the allele frequency of little n. So how often is a little n present? To do that, we'll simply take the square root of each side. So it would be Q squared square root. That equals the square root of 0.015625. And we end up that Q is going to equal 0.125. Using that information, we can figure out what P is. P, of course, representing how often the gene big N shows up in the population, because we know that P plus Q must equal 1. Therefore, P plus 0.125 equals 1, and P has to be 0.875. So what this means is that little n will show up 12.5% in the time, and big N is going to show up or be a part of 87.5% of the population. So that's our first part here. Okay, and that is solving for this, the frequency of each allele.
Graham Daniel, please come to the main office.
Sorry about the announcement, I'm still at school. All right, the next part is to figure out the percentage of the population that has each of the different genotypes. For that, we're going to use that P squared plus 2PQ plus Q squared equals 1. So, to find somebody that is homozygous dominant, we are simply going to use P squared. That would equal 0.875 squared, which would equal a 0.7656, or 76.6%. That tells us that 76.6% of our population would be homozygous dominant. To figure out who would be heterozygous, we're going to take the next term of this equation, and that would be the 2PQ. So that would equal 2 times 0.875 times 0.125, and that should equal a 0.21875, or approximately 21.9%. So that tells us that 21.9% of our population is a carrier. We've already figured out the homozygous recessive, because homozygous recessive is what we started our problem with. That would simply be Q squared, which we already know equals 0.01525, or approximately 1.6% of the population. Now, the nice thing about Hardy-Weinberg problems is that everything equals 1. So you can take your allele frequency of the recessive allele and the allele frequency of the dominant allele, and if we add 12.5 plus 87.5, we should get 100%, and we do. Over here in the second half of the problem, where we are looking at the genotypes, we should be able to take the percentage of the population that's homozygous dominant, add that to the percentage of the population that's heterozygous, and the percentage of the population that's homozygous recessive. And if we do that, we should equal 100% of the population. In this case, it ends up equaling 100.1%. The reason why it's not a perfect 100 is because we rounded within the problem. If we did not round, we would see the perfect 100%. Those are the basics of a Hardy-Weinberg problem. In class on Tuesday, we will continue to talk about these and work on some practice problems. Please make sure that you complete the survey and see if there are any questions that you have for me on Tuesday. Have a great weekend, guys. Bye.